Hi everyone, my name is Nischal. My roll number is 1801 CS33. My team has two of my friends, PV Sriram, whose roll number is 1801 CS37, and Navyasree, whose roll number is 1801 CS06. Our deep learning survey project is on image manipulation techniques, adversarial attacks, and defenses. The organization of this presentation is as follows. First, we'll give an introduction to adversarial robustness, where we'll talk about what exactly adversarial perturbations are, and then we'll talk about what is the cause for adversarial mispredictions by neural networks. And then we are going to briefly discuss about adversarial attacks, where we are going to classify the different kind of attacks. And in specific, we are going to elaborate upon white box attacks, particularly on FGSM and PGD attacks. And then we are going to give examples of adversarial attacks in the real world settings, particularly in the industry. And then finally, we are going to talk about defense mechanisms for adversarial attacks, where we are going to talk about the general methods. And then more particularly, we are going to talk about robust optimization methods. And then finally, we are going to talk about the usage of unlabeled data for improving adversarial robustness, which is also the current state of the art. And then we are going to give a brief conclusion about the topic. So, why exactly do we need adversarial robustness? Or what is adversarial attacks in the first place? We know that in the current scenario, deep neural networks are capable of a lot of things, from recognizing objects in images, like the image in the left hand side, where we can see that the deep neural network is able to identify the image for different objects like a car, a dog, horse, person, and everything else with their respective confidence scores. On the right hand side, we can see deep neural networks which are capable of recognizing faces. And then we can see an image of deep neural networks which are capable of solving captchas. So this is how deep neural networks have been evolved in the current days. And also deep neural networks and AI technology in general has become so efficient that it is able to defeat human experts in games like chess and Go, which is really a very impressive thing. So having said that, now we know that deep neural networks have been able to outperform their human counterparts in various challenges and games like Go and the ImageNet challenge. However, we still see that security and reliability are major concerns during the deploying of deep neural models in the real world. We see that deep learning models are fooled by an adversary through a small input perturbations in the original data that is as such imperceptible to the human eye. So this is one major security threat to the existence or the reliability of deep neural models in real life. So adversarial robustness as such deals with securing deep neural networks against adversarial attacks. So the goal of this presentation over here will be to talk about adversarial attacks and then proposing certain defenses for countering the adversarial attacks. So are deep neural networks reliable? This is a question we are trying to answer in this case. So we'll just have an overlook of what adversarial attacks are. Now let's see this picture over here. Here we have a symbol called stop. Let's say we are in a self-driving car and self-driving car needs to understand what is happening in front of it, the signs which is provided to it. So the stop sign is provided to it, and in general the deep neural model which is used in the car will be able to predict it as stop. But now let's say that there is a malicious attacker who tries to add a small perturbation, which we are going to define further in the next few slides, which is just a carefully constructed noise input to the original image, which is going to cause the deep neural model to be confused and predict that this particular symbol is not stop but max speed 100. So this is a case wherein the deep neural model has been attacked by a small perturbation, which is leading to the misclassification of a particular image, which is of very critical application in the real life. So this is an elaboration of what was shown in the previous slide. We can add something called as an adversarial noise to the original input image to give an adversarial image. The point to note over here is that the adversarial image looks the same for a human being. So from a human being's point of view, the adversarial image has not changed, but the deep neural network is still confused and it misclassifies the particular image into another category as compared to what it used to do earlier. So this is basically an example of adversarial attack. So this is one more example of adversarial attack where the original image is classified as a duck, but by just adding a carefully constructed noise and multiplying it by a small number 0.07, we see that the same image is being classified as a horse. From a human's perspective, nothing has changed. The human will still classify it as a duck, but the deep neural model is confused in this case. And same thing with the audio example in the bottom of the half of the slide, where how are you is added with a small perturbation, which gives rise to the perturbed input and changes to open the door for a deep neural network's prediction. So now let's come to the question as to why do deep neural networks fail. Now we can see this particular image over here. This image is basically separating, it basically shows the decision boundary of humans and the decision boundary constructed by deep neural networks for separating different classes. So here we can see that the decision boundary constructed by the deep neural networks are not exactly coinciding with that of the human beings. So adversarial examples actually come into picture over here. Now if we focus on this alpha, which is a triangular shaped object over here, which belongs to one class, and if this particular data is correctly classified by both humans as well as by the deep neural networks, but by just applying a careful perturbation, we can convert alpha to alpha dash, and we can basically make the deep neural network misclassify alpha, whereas the human is still going to look at this particular alpha input as the same class, whereas the deep neural network is now confused. So this is the basis of why deep neural networks fail, because of a difference in the perception boundaries or the decision boundaries of the deep neural networks and that of a human being. So that is the main reason. Now we are going to quickly have a look at a few trivial adversarial examples. Now, adversarial examples exist in this underfitting case. So we know that in underfitting, the model has not actually achieved its real capacity and it is not fitting the data properly, which is causing several natural errors. So here we see that due to excessive linearity, there are boundary points which are being misclassified. For example, this circle and this cross, which is labeled in red, are at the boundary and they are misclassified. If we had a nonlinear boundary in this case, then probably this problem would not have existed. So this is for the underfitting case, and now we see that this problem also occurs in the overfitting case, wherein the deep neural model has completely overfitted on the data and it is not generalizing well on the unseen data. So for this case, it is misclassifying the samples into the categories which they actually do not belong to due to the poor generalization. So one more thing we need to notice, the adversarial perturbations which we talked about, which we add to an image to convert it into an adversarially perturbed image, is not random. We may expect it to be random, but it is not random, and we have shown this through this particular video which we have self-recorded. Over here, basically we show that we vary these parameters epsilon and radius, which we'll explain in the next few slides. Basically, we are varying the perturbations and checking the prediction of the neural network for this horse image. So we see that if we just make some random perturbations, just let's say we vary the radius and epsilon randomly, the predictions of the deep neural network don't change. They still remain horse, although the confidence changes to a little bit. Probably the confidence decreases, but still, like if we make a very carefully constructed perturbation and add it to the original input, only then the deep neural network is going to misclassify it. So this is about the adversarial perturbations, and then throughout this presentation we are going to use certain terminologies for referring to the images and in general other mathematical notations. So here we have shown that here X is the original clean unmodified input data, Y cap is the model's prediction, T is the original class label, X dash is the adversarial example, which is the example which is created after adding some kind of perturbation to the original input X. Y dash is the target class of the adversarial example. So there are something called targeted attacks, wherein we can target the attacks to a particular class. So Y dash is that. F is the deep learning model itself. theta parameters of the model, delta is the perturbation generated by the adversarial algorithm, and capital delta and epsilon are the perturbation constraints because we need to perturb in given constraints. And then this is the gradient function, del operator, and then we have LP norm, which is represented by this symbol, and then we have the loss function, and D is the training data distribution, and finally we have KL divergence, which is the Kullback-Leibler divergence between the two probability distributions. So next we are going to talk about adversarial attack.
Thank you, Nischal. I'll be taking over the talk right now. And I'll be talking a little bit more about the crux of the whole survey which we're doing. So, of course, the survey deals with both the attacks part as well as the defenses, and it is important to understand how can you actually cause the attacks. Right, let's move forward. Before we talk about the attacks themselves, so there are. It is important to understand that there are various different methodologies to actually cause some sort of an attack within the deep learning models. On the broad scale, there are 4 types of attacks you can do based on various different factors. For example, timing. Whether there's a possibility of attacking during the training itself or after a test, after you have trained the whole model, during the testing, you can do the attack. So these 2 different things are known as evasion and poisoning. So poisoning is something which will happen during the training time, where you can affect the learning of the model, the weights, in such a way that it is perceptible to some sort of an attack. And evasion is like during inference time or during test time, you do some sort of perturbations to the input data to cause the error. Information. So how much of access does the attacker have? Like, does the attacker have access to the model? Do they know what the architecture is? How are the weights? What are the hyperparameters? What is the optimization, or what is the nonlinear activations which are being used? Or do they not have the access? So these 2 different things are called as white box and black box. White box obviously means that attacker has the information to the model specifications and features, even the data set also, and they can query it anytime they like. However, quite the opposite, black box is like you have no information regarding the model, but you have to figure that out by yourself, maybe through some queries, or inputting and outputting through the model. However, there's another thing called as a gray box, which lies between both of them. You know a little bit, or maybe the type of the architecture, but then you don't really know the specifications. So it's sort of like in the gray area, hence the name gray box. The goal of the attacker, right? So does the attacker just wants to confuse the model, or do they want an input to be classified wrongly to a particular class? So obviously it's called targeted attack if there's a particular targeted class which the attacker desires. If there's not, you just want to misclassify any sort of input, and it's called a non or untargeted attack. The frequency, again, like, does the attack happen in one shot? If you just do one sort of a perturbation and they cause maybe during the training time only they cause an error in the learning, it causes the model to learn differently, or is that sort of like an iterative process, like one after the other, slowly you'll be confusing the model? Of course, this sort of perturbation, whatever I'm talking about, happens on the input. So do you change the input only once, or do you change it little by little until it misclassifies? Hence, there are 2 types, like single step and iterative attacks. Moving further, now we have talked about the different types of attacks. Let's talk about the attack itself. So what are we actually desiring? So let's start with the classification task itself. So the whole point of classifying is to reduce the loss from whatever you get from the model, so that it comes as close to the target class as possible. So this is the optimization parameter which you look for in a regular classification task. However, for our particular task, what we actually desire is to maximize the loss in such a way that you can, the only thing which you can change is the perturbation. So you have to maximize the loss by changing this delta. Of course, you can't affect the weights themselves, you can only affect the inputs. So there would be no point if you are trying to maximize the loss and that is the optimization thing itself. Then it will do a hill climbing rather than the gradient descent. So it's important to understand that we are not affecting the weights in this scenario. We are just affecting the delta through which the inputs are nudged in any direction to cause the adversarial attack. So this is the parameter. We want to maximize this by changing the input is delta. Right. So if you look at the training setup itself, on the broad scale, you have theta, which is the model parameters, which are the weights, and you have the delta, which is the perturbation which you can cause over the inputs, the training inputs. So the whole setting is you want to minimize a loss by affecting the weight parameters in general, but then you want to maximize the loss by affecting the perturbation. So the perturbation causes as much as loss as possible, and so it's a local optimization for increasing the loss. But on a global scale, by affecting the weights, you want to reduce the loss. So the training on the model is happening. It is becoming more and more robust to adversarial attacks. And how that is possible is because you're doing some sort of a local optimizations in terms of parameter tuning or input data tuning. Right. So for the scope of this presentation, we'll be dealing with the white box attacks, which is like the attacker has access to the model, and you can make changes whatever based on the information that you have. So again, in a flow chart, so what are the adversaries has access to? They have access to the training data. You can contaminate the training data themselves, or you can affect the learning model in some way, or you can attack the test data. So you have access to these three things. So in a broad sense, you can change the inputs in a little bit such that they misclassify, or you can understand what the model has learned, and based on that, you can confuse it. Like if there's if you can see a clear boundary between the classes, then you can nudge the inputs in such a way that they can maybe just cross the border. So that is where the learned model will help you. Or you can do similar things for the test. You can affect the test data so that you can misclassify. Again, the three different sort of settings which I talked about. But then again, since we're talking about the white box attacks, we'll talk about the two most popular attacks in this segment. The FGSM, the fast gradient sign method, or PGD, which is the projected gradient descent. Now these two things come under actually the attack frequency type. So one is the one shot, which is a single step attack, which is the FGSM, and projected gradient descent is an iterative attack, which as we'll be discussing in the further slides. So FGSM, again, there are two types, right? You can do an untargeted attack, as in you just want the model to misclassify any sort of input data, or you want to misclassify it to a certain class, which is called the targeted attack. So intuitively, this formulation would make sense. So X dash is the affected input, or the nudged or the processed input. As in the real input, you are adding some sort of a perturbation. How what is the optimization parameter which we're looking for is that you want to maximize the loss of this between the predicted output and the actual output in such a way that the delta, whatever you add to the input, it is as low as possible. You don't want to actually, for example, as Nischal has already talked about, if there's a picture of let's just say a dog, if you put in a lot of information about a cat over it, then even to the human eye, it will look like a cat. So you want to just add as much as noise in such a way that human can still perceive it to be a dog, but then the model would misclassify it. And therefore, there's a constraint over a norm. So the norm of the perturbation which will add will be less than a certain epsilon. So you want to maximize the loss such that the perturbation is as low as possible. And coming to the targeted attack, you do the similar thing. You want to maximize the loss between the predicted and the actual label. However, you want to parallelly reduce the loss between the predicted and the targeted label. So you're putting a lot of distance between the actual label and the predicted label, and you're also making the predicted label and the targeted label as close as possible. So two things at the same time. Here as an example, so the FGSM model, like this is a pre-trained model which could properly identify this as a macaw with a 97.3% confidence. However, after adding a perturbation, which is the output of the FGSM, you can see that a completely different class, a bookcase, is being identified. But still, both to the human eye, they both look like macaws. So that is the effect or the power of FGSM. And however, we also found a really good implementation of this model online, and we have ran it in our own settings, and we can see that after doing some sort of a perturbation over a goldfish image, you can see that a chameleon is being predicted, right? Now, coming to the second type of attack, the projected gradient descent, which is an iterative step process. The formulation is again like this. So the perturbation is coming from a projection of a sort of like a gradient ascent or a hill climbing sort of an approach. So the delta is something which you are changing. The gradient, the loss is being taken gradient over the delta. So similarly, how weights are being affected in a gradient descent algorithm, you are sort of doing a similar gradient ascent in a in such a way that you are maximizing the loss. Pretty straightforward things in between the brackets. However, there's a important part, which is the projection. Why is a projection important? Like, you can do a hill climbing and get it over with, right? Well, I'll show that in a pictorial manner, uh, maybe through this example. Let us say this is the error uh, uh, function over the input data, and you can see that if there's a sample, it can classify it with much less loss. This is the areas of low loss. However, the thing which you want to do is you want to maximize the loss, but still make the input data like perceptible to human eye to be like correct. Like macaw was macaw before also. But if you just do without a constraint, right, that macaw might actually change into a bookcase with the perturbation which you're adding. So if you're not keeping some sort of a constraint over how much gradient ascent you can do, then you are actually affecting the input data, and the model is not doing anything wrong. It is actually uh, classifying a noisy data to be noisy. So you want to affect this as less as possible, which is why you use a projection, but you want to get whatever the best you can. So for example, in this particular L2 norm ball, as we say, the constraint, this is the highest loss which you can get. So the change you should be like over this. Maybe there's a higher loss outside of this ball also, but we don't want to go over there. Within a particular constraint, we want to optimize as much as possible. So that is in fact what is PGD. It's a constraint optimized problem, and you want to get a small enough perturbation that's it. You maximize the loss, and the constraint is used like usually done using the norms L infinity L2 norms. It's will like you can do that in sort of like a projection manner. Like you have the norm itself, and the nudges you will do, you'll sort of do it in the projected dimension, and then you project it back to the original dimension, the shifts. So this is the pseudocode. If you may, you can start with a random perturbation in one direction within the LP ball, and then you take a gradient step within the LP ball itself uh, towards the higher loss, and then you keep on going until you get the best highest loss within the ball. So that is what we discussed initially. Again, the importance of the ball is being shown in this particular GIF. Like you have the MNIST data, 7, the number 7, there are multiple of them, but we have managed enough to, put in enough perturbation to convert the input data to actual numbers from 0 to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this much of an effect should not happen. If you do a normal gradient ascent, right, which is like a high epsilon attack as mentioned over here. If you're doing a very high attack, then you're actually changing the input data. There's no point of an adversarial attack right now. So you don't want this to happen, which is why there should be a constraint. Again, this is not from a generator model. It is just by statistically affecting the input data, which is called the high epsilon attack. Again, we found a really good implementation for the PGD as well. In this case, the goldfish is being classified as a green lizard or a chameleon, similar sort of. Thank you. That was my part, and my friend Navya will.
So, hi, I'm Navya. Talking about the applications of adversarial attacks, we have huge applications in autonomous systems, in medical systems, and in surveillance cameras, and in various fields. So, talking about the autonomous systems, we have autonomous cars, which are basically sensing whether the traffic light signal is green or red and acting accordingly. Suppose if we insert a right amount of invisible perturbation into the DL classification system, it may classify the green light as red light and can cause dangerous accidents. And this is harmful to society. That's why this adversarial attack has critical application in the field of autonomous systems. So also coming to the deep medical system, if we insert the invisible amount of perturbation here, it can classify a benign cancer as a malignant cancer. And if we talk about the surveillance cameras, by inserting a right amount of invisible perturbation, just as if we see here, so causing the adding a little amount of pixel changes as the input to this image can make our system classify this in a wrong classification zone. So this can cause huge effects, just like it can cause a different prediction in the deep medical system. It can cause a different prediction in autonomous system. It can also be used in order to fool the surveillance cameras. So these are all the various fields. Apart from that, these adversarial attacks are also possible in the domain of 3D recognition, in audio and text recognition, and also in deep reinforcement learnings. So, talking about the audio recognition, in order for an audio signal input, up to 50 words in text translation, they can be modified by introducing a perturbing of 1% in the audio signals. So, but the non-linear effects of microphones and recorders, whatever we are using, so the perturbed audio signals do not remain adversarial after being played over the air. So the attacks have been made possible in such a way that the nonlinear effect and noise are also taken into consideration while the attack is happening. So the adversarial attack is basically defined in received signals instead of transmitted signals, and the proposed attack successfully generates adversarial audio samples in the physical world. So this is how the audio signal attacks can happen. Whereas coming to the field of text recognition, the three word level perturbation strategies like insertion, modification, and removal has been carried out in order for a successful attack to happen. So, apart from that, what this attack basically does is it first identifies the important text items for classification, and then it exploits one of the perturbation strategies on those text items. And it has been proved that these attacks can successfully fool some of the best state of art DNA classifiers we have till date. So, if we consider this example of a sentiment analysis task, so we have a text, and if we just swap our original labels, original words with the adversarial labels, so the review of the total text can change. So it classifies it in an opposite class. So the complete classifier might have a negative impact because of the small amount of perturbation which is introduced by the adversarial labels. So these applications are huge in the domain of text recognition. And coming to the deep reinforcement learning, it can also be used in order to degrade the performance of trained policies in deep reinforcement learning models. So there we have state and we have an input of the policy and the actions to be performed. So if we compute such a loss function taking into account all these three parameters, like the parameters which we use for the reinforcement learning model, and the input of the policy, and the weighted score over all possible actions. So if we could compute such a invisible perturbation using this loss function and make this attack to be happening on a trained policy which is being trained in our learning process, so we can make a successful attack happen. And this doesn't stick to it, so it also has adverse effect in the field of deep q networks. So the successful attacks can also happen there by perturbing the input states in the queue functions, so that the learning process which is using the deep queue function may give the output as such a action, so which is the best possible adversarial actions which is required. So in this way, the deep reinforcement learning models and the deep queue networks have adverse impacts because of the attacks which is happening. So these are certain applications where we can make a successful adversarial attacks.
My name is Nischal. Now we are going to talk about adversarial defenses. That is, how do we defend against adversarial attacks? So there are three popular defense methods. The first one being gradient methods / obfuscation. So in this method, what we basically do is we construct models whose gradients are not useful for attackers. So this is a way of defending the model against adversarial attacks. In this case, the model's loss function is smooth around the neighborhood of the input. And then we have robust optimization. This is one of the most popular methods wherein we are going to improve the optimization function of deep neural network itself by adding regularization terms, certified bounds, adversarial examples during training, which we are going to see in the next few slides. And then there's one more new method which is adversarial example detection. So here, instead of doing any kind of optimization, we basically detect adversarial examples rather than making neural networks robust against them. So we can do this by either detecting some kind of statistical outliers or trying to train a separate subnetworks which detect adversarial examples as such. And then we have this robust optimization methods which we are going to discuss further here in this slide. So we have a basic recap of the different loss functions which we are trying to optimize in the standard setting and in the adversarial setting, which can be seen in the right hand side over here. We know the risk for standard classification is the first equation here. The risk for adversarial setting, where we have the second equation, where we are going to like have this loss function with respect to the perturbed input delta, perturbation delta with respect to the current input x. And then we have the worst case combined risk for adversarial training, where we have the inner maximization, which involves finding out a particular perturbation maximum, finding out a perturbation which maximizes the inner loss function, whereas we try to minimize the overall combined loss with respect to all training samples. So this method involves optimization of equation 3, which involves an inner maximization and outer minimization. So this problem is a high dimensional convex optimization problem, which is not very easy to solve given its nature. And like in robust optimization methods, we have 3 ways of solving it. So first one is adversarial training. Here we approximate this equation 2 using some heuristics to find the lower bound of this equation 2. So here we try to find the lower bound of this risk for adversarial setting using some kind of heuristics. So adversarial training is the most popular way of doing robust optimization because it's practical, but still we cannot give any certification or guarantee that this heuristics will be effective against all kinds of attacks for a given network. So for that we see certified training. So in certified training, what we do is we exactly solve the inner maximization problem of equation 3 or approximate it to solvable constraints. So we need to first solve the inner maximization problem for maximizing the given loss with respect to a set of perturbations on the given input. So we try to exactly solve it. So this works on finding upper bound on the inner loss function. So certified training will be able to certify that for a given neural network and for the given set of inputs, any attack will not be able to fool the model. So that is what certified training is going to say. And then we finally have the regularization approach, in which we prevent the model from overfitting on the noise data and improve its generalizability. So this is done by either expanding the decision boundary or limiting changes in the gradient of the model. So regularization approach is about this. And then we are going to have a look at this traits. So traits is basically a paper which talks about theoretically principled trade-off between robustness and accuracy. So in this paper they have said that there is a trade-off between between achieving standard accuracy and robust accuracy. So standard accuracy means that we are classifying the samples in a standard way without any adversarial perturbations, whereas in robust case we have the samples attacked with some kind of predefined attacks, and we are going to check the accuracy of the attacked sample. So that is the robust accuracy. So robust error can in general be decomposed into natural misclassification error and boundary errors. So the algorithm minimizes the natural loss along with simultaneously shifting the decision boundaries away from the trained data points, which is what regularization generally does. So this L robust is an addition of L standard and L regularization, where beta is the term which controls the amount of the loss of the regularization which we use. So this is the main concept of traits. So here we are going to talk about one of the state-of-the-art techniques, which is using unlabeled data for improving adversarial robustness, which was published in the 32nd conference, 32nd NeurIPS conference. So the related work for this is that there has been work which shows that adversarially robust generalization requires more data. So we can see that in this particular 2 graphs over here, the green line over here shows the standard accuracy, and the orange line over here shows the robust accuracy. So here we can see that there is a constant gap in the standard accuracy and the robust accuracy, no matter whatever is the training steps. So this shows that for achieving more robust accuracy, we will require more amount of data points as compared to achieving just a good amount of standard accuracy. So there is a sample complexity gap in terms of the robust accuracy requiring more number of data points. So the authors of this paper, Smith et al., have shown this using this particular examples. They also theoretically proved it using a simple Gaussian model that there is a sample complexity gap, and that adversarially robust classifiers require more data for training. So now the central motivation of this paper, which is unlabeled data for adversarial robustness, is that from where do we get this additional data, having known that there is a sample complexity gap? Because we know that labeling data is generally an expensive and tedious process, and it takes a lot of time and money as well. So adversarial robustness also requires that the predictions have to be stable around naturally occurring inputs. So achieving this does not require labels as such. So this particular paper is trying to solve the problem of sample complexity gap using unlabeled data. So they're not necessarily labeling the data in this case. So data sets which they're using over here is CIFAR10 dataset and tiny 80 million dataset. The algorithm proposed in this paper is called robust self-training, wherein we have the labeled data initially, we have some labeled data on which we are going to calculate the standard and the robust accuracy. And now for increasing the robust accuracy, we bring in additional unlabeled data, which is represented as x1 hat to xn hat. And now the parameters are standard loss L standard, robust loss L robust, and unlabeled weight W. So first we are going to learn the theta cup intermediate by minimizing the standard loss. So we have the label data and we have a deep neural model, let's say in this case ResNet 18, and then we are going to just minimize the standard loss, which in this case is cross entropy. And then what we do is we generate the pseudo labels for the unlabeled data using this trained model. So generating pseudo labels is called self-training or active learning, in which we basically use a trained model for getting the labels for unlabeled data. So this is what we do, and then we finally learn the new set of parameters for the adversarial robust model by minimizing the robust loss. And the robust loss over here contains the unlabeled data as well, along with its pseudo labels, which was obtained from the previous step. And W is basically used for weighting the amount of effect given to the unlabeled data, because the pseudo labels may not always be very perfect, and we may want to reduce this weight W in some cases. So this is the meta algorithm over here, and these are loss functions which are used in RST or robust self-training. We know that the L standard is just the negative log likelihood, or basically the cross entropy loss. And then for L robust, we have L standard plus beta times L regularization, which was the equation which was used in original traits paper. And over here, L regularization is basically L regularization loss is the Kullback-Leibler divergence loss between the probability distribution of the original input and the perturbed input. Well, the perturbed input is basically perturbed by some perturbation in some norm space, which we defined earlier. And basically we approximate L regularization using this particular term, which is basically the Kullback-Leibler divergence between the original data distribution and the projected gradient of that particular input. So this is how the L regularization is defined. And working of robust self-training, the first is supervised training, where we have the label data in the model and we are training to reduce the error for classification on label data. And then we have the unlabeled data and we generate the pseudo labels using this trained model. And then what we do is, after generating the pseudo labels, we get a combined data which contains both the labeled data and the new unlabeled data along with the pseudo labels. So after having done that, we are going to train the same model over here. We are going to perform robust training through regularization, which was shown in the traits paper. So that is the main crux of this particular paper. Experiments, the first one is basically here we talk about how do we obtain unlabeled data. So we discussed about data sets used in this paper earlier, in which CIFAR10 is used as a labeled data set and tiny 80 million data set is used as the source for the unlabeled data. So what we do is basically we select 1 million images from the 80 million with keywords not appearing in CIFAR10 because we don't want it to clash, and then we use tiny 80 million images as source for extraction. We train a 11-way classifier, 10 CIFAR classes and 1 non-CIFAR class, and then we collect 50k images from 50k images from each class having the highest classification accuracy to form final 500k images. So from this 10 CIFAR classes of the unlabeled data, we basically extract 50k images and get 500k unlabeled images, and then finally we apply the robust self-training algorithm on the 50k labeled sample of CIFAR10 and the 500k unlabeled data which is obtained in the way specified above. So this is how the paper actually proposes, and then the results are summarized in this table here. So here in the rows we have different comparing algorithms along with the state-of-the-art method, which is RST-ADV, which is robust self-training using 50k labeled samples and 500k unlabeled samples. And on the columns we have different kind of attacks, which is projected gradient descents, and these projected gradient descents are of different kinds based on the hyperparameters used. That's why they're named as Madry, traits, and ours. Ours is basically the projected gradient descent which is proposed in this paper, and CW is Carnelli-Wagner attacks, and then the best attack. The best attack in this case is PG hours attack, and then no attack. No attack means that it's a standard classification basically. So here the unsupervised fraction is 0.5. In the final RST-ADV experiments, unsupervised fraction is 0.5 and the learning rate schedule is cosine, and the model which they're using is wide ResNet. So wide ResNet is a popular model. So the model used for all the experiments is wide ResNet 2810. Here we can conclude that RST gives the best results both for adversarial classification as well as standard classification as compared to the other adversarial training algorithms. RST-ADV, which is the proposed method, gives the best result for both adversarial classification, which is 62.5, and also for the no attack case, which is a standard case. So in conclusion, we can say that deep neural models are not reliable and are prone to misclassifications by carefully constructed inputs. Adversarial perturbations as such are not random and can be generated using various attack mechanisms. Adversarial robustness of models is very important while deploying it in the real world. And then several defense mechanisms exist for tackling adversarial attacks. And finally, we have seen that unlabeled data actually helps in improving adversarial robustness. And also we saw that unlabeled data can help in improving the standard accuracy as well, apart from actually increasing the robust accuracy. So this is the conclusion of our deep learning survey.